Hi, I am Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the types of superconductors. So, in this session, we are going to cover the topics type 1 superconductors, type 2 superconductors, and then differences between the type 1 and type 2 superconductors. Then we should see the differences. So, types of superconductors. So, in these types of superconductors, first of all, what is the critical magnetic field? Here, critical magnetic field means that at which magnetic field the superconductor converted into normal conductor. So, in the presence of critical magnetic field, a superconductor converts into normal conductor. So, based upon the conversion process, superconductors are classified into two types. So, based upon the conversion process, these superconductors can be classified into two types. In that two types, type 1 superconductor and then type 2 superconductor. Type 1 superconductors and then type 2 superconductors. So, when say this type 1 superconductors, let we take a cylindrical superconductor, and this cylindrical superconductor is placed in the magnetic field H, so along the axis of its superconductor. Okay, so it will not allow the magnetic lines and obeys a Meissner effect. So that is H is equals to minus M. In the last session, we have seen that what is Meissner effect. So in this Meissner effect, the superconductor does not allow the magnetic lines to pass through it. So this was observed by the Meissner, so that we call that as a Meissner effect. Here, we are considering a cylindrical superconductor to which a magnetic field H is applied along the axis of it. So, when placing in the magnetic field, the superconductor will not allow the magnetic lines and it obeys the Meissner effect. So, that is H is equals to minus M. So, H means that applied magnetic field. Applied magnetic field, M is the magnetization. Where H is the applied magnetic field, M is the magnetization. Where here H is equals to minus M. So H is equals to minus M means that the H applied magnetic field is equals to minus M. So that is minus M is magnetization is oppositely working to the applied magnetic field. So opposite direction, that magnetization is acting. In the opposite direction, the magnetization is acting to the applied magnetic field. So inside the superconductor, the magnetization acting is opposite to the field. When the magnetic field is equal to the critical magnetic field Hc, then immediately minus M becomes 0. Minus M, the magnetization becomes 0 and magnetic lines immediately penetrate to entire superconductor and converts it into normal conductor. So, when the magnetic field is equal to, that is magnetic field H is equals to the Hc, critical magnetic field, then immediately this minus M becomes 0, so that magnetic lines immediately penetrate through the superconductor and it converts it into normal conductor. So in this case, the conversion is very fast. In this case, the conversion is very fast and is known as type 1 superconductor and also known as a soft superconductor. Soft superconductor. So, we can take the examples strontium, tin, hydrogenium, that is mercury, niobium, vanadium, etc. We can take examples for this type 1 superconductors, that is soft superconductors. So in this diagram we can clearly observe that we are taking a cylindrical superconductor. This is a cylindrical superconductor. So this is placed, or we are applying some magnetic field. So this is the magnetic field we are applying along the axis of this superconductor H. So magnetic field applied to this superconductor. These magnetic lines are not passing through the superconductor. So these magnetic lines are not passing through the superconductor because here the magnetization is oppositely working to the applied magnetic field. This magnetization oppositely working to the magnetization oppositely working to the applied magnetic field, so that it is in the reverse direction, so that no magnetic lines are passing through the superconductor. So this is the figure of superconductor, which is H is less than Hc. H is less than Hc. So that is the applied magnetic field is less than the critical magnetic field. Applied magnetic field H is less than the critical magnetic field. So in this case, a superconductor does not allow the magnetic lines to pass through it, as its magnetization is oppositely acting to the applied magnetic field. H is greater than Hc. At H is greater than Hc. That is applied magnetic field. Applied magnetic field is greater than the critical magnetic field. Applied magnetic field is greater than the critical magnetic field. So here So when keep on increasing the applied magnetic field above the critical magnetic field, the magnetic lines, can pass through the conductor. So at this case, minus M becomes 0. Minus M, the magnetization, opposing magnetization becomes 0, so that the applied magnetic field can pass through the conductor. So it converts into normal conductor. So that's why here, when the magnetic field is equal to the critical magnetic field Hc, then immediately minus M becomes 0. So here here HC is greater than equals to HC. So what happens when H is equals to HC? Minus M becomes 0, so that the applied magnetic field can pass through the conductor, and it converts this superconductor into normal conductor. So the variation of minus M with H. So the variation of magnetization with respect to H. Variation of opposing magnetization with respect to H. So when taking applied magnetic field on x-axis and the opposing magnetization on y-axis, so the superconducting, that is H is less than HC. Here the region is H is less than HC. It shows a superconducting state. It shows superconducting states, and where H is equals to HC, so the minus M falls to 0. Minus M falls to 0. Here minus M becomes 0 here, so that the superconductor converts into normal conductor, so that the magnetic lines penetrates through the superconductor. So that after H is greater than or equal to HC, it acts as a normal conductor. So this is superconducting state where H is less than HC, where H is greater than equals to HC, it acts as a normal conducting state or normal conductor. So where H is less than HC, it is in the superconducting state. Where H is greater than or equals to HC, it is in the normal conducting state. Normal state. So why? Because of here, when H is equals to HC, so minus M becomes 0, so that the magnetic lines immediately penetrate through the superconductor, and it converts into normal conductor. That's why it converts into normal conductor. Type 2 superconductors. So consider a spherical superconductor as shown here in the diagram. So considering a spherical superconductor which is in the field, magnetic field H. So as per Meissner effect, the magnetic lines not pass through the superconductor. So as per Meissner effect, it expels the magnetic lines, and H is equals to minus M. So the magnetization inside a superconductor, opposes the passage of lines through it. Opposes the passage of lines. Lines means that magnetic lines. So the magnetization inside a superconductor opposes the passage of magnetic lines to pass through it. So here we have a mark. So at the end of at both the end of the spherical superconductor. Okay. So the curved magnetic lines are concentrated at the two ends marked as cross, as such that intensity H is predominant at those ends up to lower critical magnetic field HC1. then the penetration starts at those end marked as cross. So because the intensity at those ends reaches HC1, critical magnetic field 1 value at first. As a result, minus M value, that is opposing magnetization value, decreases and the penetrated portion loses superconductivity and becomes as a normal conductor. So this conversion is usually completed at HC2. So the conversion of superconducting state to normal conducting state completed at HC2, critical magnetic field 2, that is upper critical magnetic field. So where the penetration covers the entire surface. Before that, it is going on to penetrate, that is the at HC1, the penetration starts at HC1, that is lower critical magnetic field, whereas HC2 upper critical magnetic field. Upper critical magnetic field. So where H is less than HC1, H is less than HC1, it is in the superconducting state. At H is equals to HC1, H is equals to HC1, it starts penetrating of magnetic lines. So that is minus M slowly decreases. The opposing magnetization slowly decreases, so that the conversion starts here from superconducting to normal conducting state. So here penetration starts HC1. Penetration starts to convert superconducting to normal conducting state. So when the value is minus M value is goes on decreasing and the penetrated portion loses superconductivity and becomes as a normal conductor. So this minus M goes on decreasing and becomes to 0. Minus M goes on decreasing and falls to 0. Then the superconductor loses its superconductivity, so that all the superconducting portion, all the superconductors, the portion which is penetrated, the magnetic lines, wherever it is penetrated, so that portion loses its superconductivity and becomes as a normal conductor. So this conversion is usually completed at HC2. So when H is equal to or greater than equal to HC2, when applied magnetic field H is greater than HC2, the superconductor completely converted into normal conductor. so that the penetrated portion loses superconductivity and becomes as a normal conductor. So between Hc1 and Hc2, it has a mixed state of superconducting as well as normal conducting state. After Hc2, it is converted into normal conductor. The variation of opposing magnetization with H we can see in the diagram, and in the case of conversion is slow. In this case, the conversion is slow and is known as star 2 superconductors. They are also known as hard superconductors. For example, we can take niobium, germanium, etc. for the type 2 superconductors, which is the hard superconductors. So this is the superspherical superconductor which is placed at the magnetic field. So with respect to magnetic field, how the magnetization is varied, and regarding to that, how the magnetic lines can pass through the superconductor. So in the figure A, this is a superspherical superconductor, and where H is less than Hc1. H is less than Hc1. So Hc1, we know that this is a lower critical magnetic field. So H is the applied magnetic field. So when this spherical superconductor is placed in the magnetic field H, so this superconductor is placed in the magnetic field. When applying magnetic field up to the value of Hc1 or below Hc1, the superconductor does not allow the magnetic lines to pass through it. Why? Because the magnetization is opposing the applied magnetic field, so that it is opposing the applied magnetic field. Whereas in the second diagram, figure B, where H is less than equals to Hc2. So Hc2 is the upper critical magnetic field. So H is less than equals to Hc2. So what happens here? As at Hc1, when H is equals to Hc1, the penetration starts. At H is equals to Hc1, the penetration of magnetic lines starts up to H is less than equals to Hc2. So the intensity may be increases to penetrate as the magnetic field increases or decreases. Here, in this case, the magnetic lines are slightly passes through the superconductor. As here H is equals to minus M, but this minus M is not equals to 0. It is not equals to 0, but the minus M opposing magnetic field is weaker. That is, it is decreasing. The magnetization, opposing magnetization is decreasing, goes on decreasing, so that a somewhat intensity of magnetization, that is magnetic lines, are passing at the end of the superconductor. That is at the end of the both the ends of the superconductors marked with cross. That is, here some of the magnetic lines are ejected and some very less amount of magnetic lines are passing through the superconductor, which is at the ends of the superconductor. So here in this case, where H is less than Hc2, it acts as a superconductor as well as normal conductor. When coming to the figure C, normal conductor, H is greater than Hc2. That is, applied magnetic field is greater than the upper critical magnetic field. The opposing magnetization is equal to 0, so that magnetic lines can pass through the superconductor. So when minus M becomes 0, immediately the magnetic lines penetrate through the superconductor and it converts into normal conductor. So here this superconductor completely changed to normal conductor, completely converted into normal conductor from the state of superconductor. So from this diagram, so minus M, variation of minus M with respect to H. So wherever here, when H is increasing, when magnetic field, applied magnetic field goes on increasing, so the superconducting state shows up to Hc1, lower critical magnetic field. So here the state is H is less than Hc1. So at H is equals to Hc1, penetration starts. So it shows superconducting state as well as normal conducting state. Normal. So the superconducting state also be there, and also normal conducting state also. So here where H is equal to Hc2, H is equals to Hc2, minus M becomes gradually to 0. So here minus M is equals to 0, where it is at H is equals to Hc2, so that it allows the magnetic lines to pass through it and converted into normal state. Before that, that is H is Hc2. It is being in the mixed state. So from the variation of opposing magnetization with respect to applied magnetic field H, the penetration starts at Hc1. So up to Hc1, it is in the superconducting state, and it does not allow the magnetic lines. Where it touches Hc1, H is equals to Hc1, then the magnetic lines penetration starts and the conversion process starts slowly, so that it shows superconducting state as well as normal conducting state. So Hc1 to Hc2, it is a mixed state, so that it shows superconductor as well as normal conductor. After Hc2, it completely converted into normal conductor, so that here it can passes the magnetic lines to pass through. Coming to the differences between type 1 and type 2 superconductors. So type 1 superconductors, here in this superconductor, when the applied magnetic field is equal to the critical magnetic field, the immediately it converts into normal conductor. So in type 2 superconductors, when applied magnetic field reaches lower conversion starts, and it is completed slowly at upper critical magnetic field. But here in type 1, immediately it converts into normal conductor, but here in type 2, it slowly converts up to critical magnetic field. So in type 1, it has a single critical magnetic field, which is Hc. Here type 2, we have two types of that is two critical magnetic field values, that is Hc1 and Hc2. Whereas in the type 1, here there is no mixed state. It is directly converted into normal state. But here in type 2, there is a mixed state which shows superconducting state as well as normal conducting state. These type 1 superconductors called as soft superconductors, whereas type 2 called as hard superconductors. In type 1, materials with pure form are taken as type 1 superconductors. Materials with impurities or alloys are of type 2 superconductors. So these are the differences between the type 1 and type 2 superconductors. So the references are Engineering Physics by Tyagarajan, McGraw-Hill Education Private Limited, New Delhi. A textbook of Engineering Physics, M.N. Avadhanulu, P.G. Kshesagar, S. Chand and Company, New Delhi. Engineering Physics by Dr. M. Armugam, Anuradha Publications, Chennai. Engineering Physics, P.K. Palanisamy, 4th edition, Cited Publications, Chennai. So these are the references for this topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.